Hello, I'm Dr. Maurice Dupre, and in this section we're going to discuss tangent planes and normal lines. Well, to begin, let's consider the function capital F of three variables. So we'll have the variable w equals capital F of x, y, z, and we'll suppose this function has domain capital D. And let's also consider capital S, a surface inside the domain of capital F. And we're going to think of that surface as given by a simple equation where we just choose a constant and set f of x, y, z equal to that constant. So any choice of that constant leads to some set of points inside the domain for which that equation is true. And let's just suppose that that equation defines a surface. And of course, that surface will have to be inside that domain. So the domain D is some solid region of three-dimensional space. And here inside that solid region pictured here, which the solid region, of course, has a handle and it's complicated, but the surface could also be very complicated. Inside D, it could have several handles, but it's a surface, so it's more tube-like in general. And another thing we could do is consider inside that domain curves which are parameterized. So here in yellow I've drawn a curve r equals r of t. And so having it parameterized in particular, we could think of it as a motion if we would like. Now, these three things, the curve inside the domain, the function, and the surface given by f of x, y equal f of x, y, z equal constant, are ingredients which allow us to work out tangent planes to surfaces. And so let's see how this works. To begin, we want to examine the chain rule. Remember, the curve is parameterized by r of t, so in effect, thinking of that as a position vector of a point, I can put it into the function f because all the position points are inside the domain. And so then f of r of t depends purely on the parameter t, and so I can differentiate with respect to t. And the chain rule tells me, gives me a very nice formula relating the gradient vector del f at the point r of t dotted with r prime of t to the derivative. It just says they're equal. To differentiate f of r of t with respect to t, take the gradient vector of the function capital F at the position and dot it with, in effect, the velocity vector. So for short, I've written this df dt equals del f dot v. Now, suppose the curve C lies entirely inside the surface. So you imagine that the curve is in the surface. Since on the surface f is constant, if C, the curve, is in that surface, then f of r of t itself is constant, and so df dt will have to be 0. And so what that then tells me is the gradient vector dotted with the velocity vector is 0. Well, what does it mean when vectors have dot product 0? It means they're perpendicular. So here, the gradient vector for the function f is perpendicular to the velocity vector of any motion through that surface. Well, let's look back at our picture now. Ask ourselves, what does that really mean? Here I am at some point on the surface. Let's think right there. And maybe the curve is actually on the surface there. And so here the gradient's pointing in some direction here. Let's think of it as coming out of the blackboard at us. And there's our gradient vector, del f. What about the velocity vector to the curve? It's pointing tangent to the curve, but see, since the curve actually lies in the surface now, a tangent vector to the curve is also tangent to the surface. And so what that's telling us then is the gradient vector for the function capital F has to be perpendicular to the tangent vector to any curve which lies in the surface itself. Well, notice if I take any tangent vector to the surface, maybe I choose for instance, that little tangent vector to the blue surface, the blue-green surface, well, all I have to do is move along the surface so that I hit that point with that as my velocity vector at the instant I hit that point, and what I've just done tells me that the gradient is perpendicular to that tangent vector. So what we've reasoned by this method of reasoning is that the gradient vector itself has to be perpendicular to every vector tangent to the surface. In other words, whenever I take a surface of the form f of x comma y comma z equal constant, if I want to get a vector which is normal to the tangent plane to the surface at a particular point, the gradient vector does it for me. What could be easier? You want to find the equation of the tangent plane at a certain point? Well, you've got a point on the tangent plane, namely the point of tangency. What else do you need? A normal vector. How do you get it? Compute the gradient at that point of tangency. That gives you the normal vector. And of course, once you have that, you can easily write down the equation of the tangent plane. Well, we'll work some examples of tangent planes and normal vectors next. Now let's work a problem where we find the equation of a tangent plane to a surface at a specific point and the unit normal vector at that point, and where the surface is given to us by an equation. So here, for the surface, with equation x squared y z squared plus y squared z equal 30, give the unit normal vector at the point 1, 2, 3, and the equation of the tangent plane at this point. You might notice that if in the original equation x squared y z squared plus y squared z equal 30, if I substitute x equals 1, y equals 2, z equals 3, this is going to become 2 times 9 is 18, 4 times 3 is 12, 18 and 12 is 30. So this is indeed a point on the surface given by that equation. So our technique, remember, is we look at the expression which is on the left side of the equation involving all the variables. And incidentally, if you had variables on both sides of the equation, you would just move them all to one side, so then the equation takes the form some expression in x, y, and z equals a constant. In fact, if you move the constant over, you can always make that constant equal to 0. It won't matter. The point is, here I have the function f of x, y, z equal x squared y z squared plus y squared z. And so the equation of our surface then is taking the form f of x, y, z equal 30. So our technique is to compute the gradient of the function f, because remember, the gradient vector is always perpendicular to the surface f equals constant at any x, y, z. And so we compute the gradient vector. So its first component is the partial derivative of our function with respect to x. Well, the only term having x in it is our first term. The derivative of x squared is 2x. The y and the z squared get treated as constant, so the first term is 2xyz squared. In the second component of the gradient, we're going to take this expression and partial differentiate with respect to y. So here in the first term, we just have y to the first power, and so consequently the partial derivative with respect to y is x squared z squared, plus the derivative of the second term with respect to y. The derivative of y squared is 2y, and the z follows along, treated as a constant, so we get 2yz. And now for our last term, we're differentiating with respect to z. X squared y is treated as a constant. Derivative of z squared is 2z, so we have 2x squared yz for our first term. And then here for y squared z differentiated with respect to z, the y squared being treated like a constant, we just end up with y squared as the last term for our last component of the gradient. So there it is. Notice the gradient is a vector-valued function of all three variables in this case. So what we want to do is evaluate this gradient at the point 1, 2, 3, because we know that that gradient vector is perpendicular to the surface at that point. So that means everywhere I have an x in this expression, I replace it by 1. Everywhere I have a y, I replace with 2. Everywhere I have a z, I replace with 3. And so there's the results of doing that, which is easy to do. For instance, 4 times 3 squared, that's 4 times 9, or 36. Here we would have 9 plus 12 is 21. And then in the last term, we'll have 12 plus 4 is 16. So there's the components of our gradient. Now, notice that the gradient vector itself, when we've evaluated it, we just get an ordinary vector. It's got numerical components. What we know at this point is that that vector is a normal vector to the surface at this point, 1, 2, 3. And so consequently, if I want to write down the equation of the tangent plane, let me just erase this line. It just depends on this statement itself. If I had arrived at that result, I can immediately write down the equation of the tangent plane because these components of the normal vector become the coefficients. So I just write 36 times x minus 1 plus 21 times y minus 2 plus 16 times z minus 3 equals 0. Now, I don't think anything could be much easier than that when it comes to simply getting an equation of a tangent plane from a gradient vector. In other words, when you look at that statement, the point of tangency is right there, the normal vector is right there, and so you can easily translate this into that expression and set it equal to 0. Now, proceeding from this gradient vector, since we know it's normal to the surface at the point 1, 2, 3, to get a unit vector, we simply have to compute its length and divide the gradient by its length. So the length of the gradient vector at the point 1, 2, 3 is just the square root of the sums of the squares of its components. So square root 36 square plus 21 square plus 16 square. And we add those up and we get 1993. So the square root of 1993 is the length of this gradient vector at the point 1, 2. Now our normal vector, our unit normal vector, capital N here, is then the gradient vector at the point 1, 2, 3 divided by its length, which is then equal to the vector with components 36, 21, 16 divided by the square root of 1993. And of course, that operation of dividing a vector by a number is accomplished by simply dividing each component by that number. And so there we have the final result for a unit normal vector to the surface at the point 1, 2, 3. Well, since the gradient vector del f at x, y, z is always normal to the surface f of x, y, z equal constant, we can use this fact to actually find a tangent vector to a curve of intersection of two surfaces. So in this problem, we want to find a parameterization of the line tangent to the curve of intersection of the surfaces having equations xyz plus xz squared equal 3 and x squared y plus y squared z equals 6 at the point 1, 2, 1. Notice each one of these equations is the equation of a surface, and so consequently they should intersect in some curve. And how about this point 1, 2, 1? If I put x equal 1, y equal 2, z equal 1, this is 2, this is 1, 2 plus 1 is 3, so that point is certainly on this surface. And if I take x equal 1, y equal 2, z equal 1 here, I get 1 times 2 is 2, plus 2 squared is 4 times 1, 2 plus 4 is 6, so 1, 2, 1 is definitely on this surface. So this point is definitely on both of these surfaces, and therefore is some point on the intersection of those two surfaces. And It's, of course, difficult to picture what those surfaces would be, but there's some surfaces and they intersect into some curve most likely, and in order to see that that's the case, if we look at the gradient vectors at that point to the two functions that define those two surfaces, then if those gradient vectors are not parallel, then it means that those two surfaces do in fact intersect at a curve. So here I've drawn a blue-green surface indicated, think of it as kind of some rubbery sheet, and here in black another surface, some other rubbery sheet, and think of them as intersecting in ghost-like fashion in some curve that I've drawn in yellow. And here at a particular point, what we want to find is the tangent line to that yellow intersection curve. And so what we need to find in order to do it is a vector tangent to that curve. Well, one thing to notice is that since that curve lies in the surface indicated in black, which is capital F equals some constant C sub 1, that means the gradient of F being perpendicular to the surface at that point is also perpendicular to the curve and therefore to its tangent vector. The same argument applies to the blue-green sheet. It's given by some equation capital G equals constant C2, and so the gradient of capital G is perpendicular to the blue-green surface at that point, and therefore, since the curve lies in the blue-green surface, it's therefore also perpendicular to that curve and its tangent vector. So consequently, if I'm just looking for a vector tangent to the yellow curve, I know that it has to be perpendicular to this vector and perpendicular to this vector. Now, whenever you want to find a vector that's perpendicular to two given vectors, if they're not parallel, you know what to do. Just take the cross product of the two vectors. So we have the gradient of F at the point P, the gradient of G at the point P. We simply form their cross product and use that as the vector V, which we'll use to parameterize the tangent line, and so consequently the parameterization of the tangent line is simply r of t, vector r of t as a position vector is the vector OP, where O is our origin, plus any scalar t times the vector v. In other words, using t as the parameter, we have a very simple parameterization. So the scheme then is compute the gradients of each of the two functions defining the surfaces, compute it at the particular point we're interested in, the point 1, 2, 1, form the cross product, and use that as the tangent vector to the tangent line. Okay, so first then, our first equation was xyz plus xz squared equals 3, and so consequently the function of three variables for which we want to compute the gradient is capital F equal xyz plus xz squared. And so to compute the gradient, we simply form the vector of partial derivatives. Here is the partial derivative with respect to x. In other words, differentiating the first term with respect to x, we just get yz. Differentiating the second term, we just get z squared. So it's yz plus z squared. Differentiating with respect to y here just gives us xz, and over here nothing. So the middle component is simply xz. Differentiating with respect to z in the first term, we get xy, and in the second term, derivative of c squared being 2z, we get 2xz. So there's our gradient for the first function, this function in effect equaling 3, defining our surface. And so we compute that gradient at the point 1, 2, 1. So we put x equals 1, y equals 2, z equals 1 everywhere, and so we just get 2 plus 1, 1, 2 plus 2. In other words, 3, 1, 4. Now the other function that we're dealing with is x squared y plus y squared z. So I've denoted that by capital G because the second surface was x squared y plus y squared z equals 6. So we need to compute the gradient of this function at the point 1, 2, 1. So again, computing partial derivatives, the derivative with respect to x of x squared is 2x, y treated as a constant, 2xy, comma. Differentiating with respect to y, we have x squared plus 2yz. Differentiating with respect to z, nothing here, and the derivative of z being 1 and the y squared treated as a constant just leaves the y squared. So when I put x equal 1, y equal 2, z equals 1, 2 times 2 is 4, and here 1 plus 2 times 2 being 4 again, z is 1, so 1 plus 4 is 5, and then 2 squared is 4. So there's our second gradient that we're interested in. And remember, what's our strategy? We have to calculate the cross product. So in other words, I want to compute the cross product of 4, 5, 4 angle brackets with 3, 1, 4. And of course, the order in which we do this is totally immaterial because we're looking for any tangent vector. And so remember how we do this, in effect, with the determinants. And so that means the gradient of f cross gradient g at the point we're interested in. Well, to get the first component, all I do, cover up the first column and look at the little 2 by 2 determinant here. 1 times 4 minus 20, that's negative 16. For the middle one, cover up the middle column, take the determinant. So 3 times 4 is 12, minus 16, that would be negative 4. But remember, for the middle one, we have to reverse the sign of that, so it becomes plus 4. And for the last one, the determinant is 3 times 5 is 15, minus 4 is 11. So the tangent vector we get is negative 16, 4, 11. Okay, so finally then, since we now are going to use this vector as our vector v, tangent to the curve of interest here, the intersection of the two surfaces, all we have to do is use this vector and the point of tangency 1, 2, 1 to write down an equation of a line. And so that's easy to do. It's just r of t equals angle 1, 2, 1 plus t times negative 16, 4, 11. You have the parameterization. Of course, it's easy to rewrite that in terms of 3 parametric equations. And so that's the process for finding tangent lines to intersection curves given as the intersection of two surfaces where you only have the equations of the surface. Notice it would be very problematic if you wanted to try and do this by using a strategy of saying, well, let's find a parameterization of the actual intersection curve. That would be very difficult to do here because you'd end up trying to solve equations simultaneously in 3 variables, 2 equations, and it could be, really very possibly impossible to do in actuality in closed form. So this method of using the gradients is the way to go here.